All right, welcome to another example. In this example, we have some keywords which will help us understand which model to use. So let me get a red pen here so I can write on the blue. It says a larger dose of heparin is eliminated, that's a keyword, at a rate of 22.5% per hour. The patient was injected with 1,400 units at 0800 hours. So the first thing I'm to do goes with my first goal, which is to be able to write an equation. And we are going to use the models in our notes to do this. So from our notes, we found that we had the formula P of T is equal to, we have four different options. So it does not mention a half-life, so it's not that formula. It does not mention a doubling time, so it's not that formula. And that leaves us to pick between the exponential model or the drug breakdown model. And it is a med, it's heparin, so that might lead us towards the drug breakdown model. But more importantly, in the drug breakdown model, we need to know the rate per a unit of time, and that is exactly what we know here. We know that it was 22.5% per hour. We did not have a continuous rate. We had a rate per a unit of time. So that is what leads me clearly to the drug breakdown model, which is the model that we used already last week. So I write that model from my notes, and then I want to plug in some values. So we noticed key values as we read through. So we'll write P of T. We'll replace P0 with the dose of 1,400 units. In the parenthesis, we have R, which is the percent as a decimal. So 22.5 divided by 100 equals 0.225. And we noticed it was eliminated, so I'm putting a negative 0.225. And T for time. So I am going to do the math there inside of that parentheses just to clean it up and make it a little nicer to work with. So the population of heparin at some point in time started with 1,400. The math in the parentheses gives me 0.775 and T as the time. So that is my answer. That's my formula for the entire of the rest of the problem. We still have two variables in that formula. So P of T, it will calculate the population of heparin for us. And we still have T, and then we can check different times as we want the amount of heparin. So we move on to question 2 here in the beige box. And in this one, it asks us how many units will remain in the patient at 1,300 hours. So I'm going up to the start here where it started at 800 hours. So I'm going to count on my fingers. So 9, 10, 11, 12, 13. It looks like 5 hours. So if I take, we can also do subtraction. So 1,300 hours minus 800 hours would give us 5 hours, no matter how we want to do that. So that means I know time is 5. Okay. So looking at my formula, P of T, population at some point in time, will be 1,400.775, and I'm going to replace the T with 5. Now I'm going to put that in my calculator. So 1,400 times 0.775 to the, so using that caret key, fifth. All right, so just go ahead, type. And I got an answer of 391.414, etc. units. We're not told how to round, so let's go to a whole number. So let's say 391 units remain. So that step is all calculator work, going back to things we learned at the very beginning of the course, like using our caret key for an unknown, for an exponent bigger than 2. We get to our final question, question 3 here in the gray box. When will the patient have only 30 units remaining? So this 30 units, that is a population or amount of heparin at some new point in time. So this 30 units is a P of T value. And that entire P of T gets replaced by a singleton number. So 30 equals, we had the 1,400 as the start, base of 0.775, and this time our exponent T remains unknown. So from here, we are going to solve using Desmos, but you may also solve using algebra and a logarithm. In Desmos, we need to turn each side into its own equation. So this is y equals 30. And this side is y equals 1,400 times 0.775. And Desmos likes x, so to the x power. So let me find Desmos here. Almost got it. There we go. And you can see I still have an old problem typed in here, so we'll clear those out. And so our first equation here is y equals 30. And our second equation, y equals 1,400 times 0.775 to the x power. And so I see two graphs show up on my screen. One of them, the second one I typed, is the exponential function. That's got the iconic curve to it. And the purple one here is the straight line across. And so we see them meet, and I click on that point. And so I have my answer, 15.077 and 30. So 15.077, 30. And we know that's an ordered pair, so x and y. We were solving for x. So when will the patient have 30? At 15, I'm rounding that off, hours after the dose. And so that would be 15 hours after 8 a.m., and we could figure out exactly what time it is, but approximately 15 hours later. So in this one, we went through all three of our outcomes for today's lesson. We wrote an equation here in the orange box, step 1, based on the models, which you do not need to memorize. Step 2, we used the numbers given and put that on our calculator to get an answer. And step 3, when the time is unknown, is when we use Desmos. So we don't use Desmos every problem, only if we do not know the time.